Okay, everyone. The topic today we're going to talk about is the gradient and the divergence in spherical coordinate system. So we define a vector field F, and three components is P, Q, R, and a Cartesian coordinate with x, y, z components. And we define another scalar function is called little f, and also with x, y, z components. So we all know that the gradient f is we do partial derivative with x, y, and z and have a vector. It is a vector form. And divergence is we do partial derivative for p, q, r with x, y, z and add them up. But what is if it is with the component is r, theta, and y. So we're going to do is we want to find the gradient and we want to find the divergence of vector field and scalar function in spherical coordinate system. So first we want to know the gradient in spherical coordinate system, and we know that total differential is this. This is what we define total differential, and we know that for an arbitrary PR we can define as this. And since we know these two, and we know df is gradient f dot, the dot product of gradient f times the dot product of gradient f with PR. So we can know that gradient f is this, and so we check the r component is times this, and the r cancel out, and we have PR. So it is. So we have this, and this times this equals to this, and this times this equals to this. So this is the gradient form of spherical coordinate system. And, okay, so the second part we're going to do now is we want to find the divergence in spherical coordinate system. So the main concept or the formula we want to use is we want to use this formula. The limit when x approaches 0 and the flux divided by the value equals to the divergence. And so we want to find every side of the infinite small area. So how many sides and what sides are there? So we want the side is we can see that a side is like this. There are two sides when r when r is different, and there is two sides when the phi is different, and there is two sides when theta is different. So we can change it. We can change this into. So for example, we only do r. So for example, like this. For example, we want to do this, and we can take out the vector, and the vector is only the directional vector is n. Okay. And S is only a scalar. So and then we can continue. We can have the S into the cross product of the r theta cross r phi, and this is the A, which the A is the theta times the phi. So the directional vector n is r. There's the direction r in when you want to calculate r. So it is change this one and everything is the same. Okay, so this is the form we want to derive. And maybe we can, and because we don't know the components of f because we don't know the components f in this, so we just change, so we just define the component of f when r is AR. So we change it into R, AR, and everything is the same. Okay, so if we want every side for the R side and for the theta side and the phi side, we need to calculate every cross for R theta times R theta cross R phi and RR cross R theta and RR cross R phi. So if we want to calculate these three, we need to have the position vector and which is this form, and we need to differentiate it with R, theta, and phi in this three, and we just do a cross, and we have this is the three components I, J, K, and we just have the dot product and we just have the length here. The length is R squared times sine phi, and this is the length is R. So after we calculate this term for RR times R theta and RR times R phi and R theta times cross R phi, and after we derive this to this and to this, so what we're gonna do now is we want to find the actual R component term. So what we're gonna do is we want to find the divergence in spherical coordinates, and we take R components for example. So we know this, and we have the value of this is R squared times sine phi, and from this line to this line we change this stands for volume, and the volume we use the triple integral, and f of x we take 1, and there is R squared times sine phi and dr d theta d phi. Okay, this is a triple integral to calculate the volume of the sphere, and this is the same as this is simply just this thing for R components. So we notice that there is a limit when R approaches 0, and we find that this equals to 0. Approaches 0, and this approaches to 0 as R approaches to 0. So we can use 罗必达 rule. So we need to differentiate the upper and the below. Okay. So by 罗必达 we just differentiate above, and we only differentiate the thing with R, make the thing with R. So this is not R related. So we just differentiate this part. And for the below, we differentiate this, and we find the result is this. And the boundary of this one for R is 0 to R, and for this is 0 for theta is for 0 to 2 pi, and for this is 0 to pi. So if we differentiate this, and by the fundamental theorem of calculus, and we find out that it is just this, so from this we differentiate to this. Okay, so we finish the 罗必达 rule, and this is the result. And since we preassume this is differentiable, so we can do this, which means this is continuous. Since we preassume this is differentiable. So we can take this out because when r approaches 0, this becomes a constant as it is continuous. You can see this as a constant, so we take this out. And we have everything else here. And for this, and for below, we just simply take out the part that is component for theta and phi, take out, and this is the thing same as up. So we just cancel out this two. Okay, so we have found that this line is equal to this line. We have found the divergence of any vector field, and we found the r part, the r component. But there is still phi component and theta component. So we need to calculate them. If we calculate them and we use the same method, if we use 罗必达, and we use this formula, and we found when we calculate this, and we have the same, everything is the same, and 罗必达, and we use the same condition, and we will find out that the components of phi is this, and the component of theta is this. So the whole divergence in spherical coordinate system is this line. It's much different from the Cartesian coordinates, but it is very interesting. So this we can also use it in cylindrical coordinate system, and which is very useful in electrodynamics if we want to calculate like something like Gauss law or like anything that needs in 3D space. Okay, so this is the video. Thank you.